All right, determinants and linear independence. Um, Linear dependence, right, of vectors can be not so bad to show. To demonstrate that vectors are linearly dependent, you just need to say, hey, look, this one can be expressed as a linear combination of these other ones, and you're done, right? You find some very concrete, very specific linear combination, um, and you've done it. You that of some of your vectors that equals the other. There you go. They're linearly dependent, right? Linearly independent can be trickier to show, right? Because you have to show that it's impossible for any one of those to ever be expressed as a linear combination of the others. Sometimes you could do this, maybe with algebra, set up a system of equations. Um, maybe you could do it, right? But it can be more difficult to prove a linear independence, right? Um, Fortunately, there's a nice theorem, a very convenient theorem called the Vector Independence Theorem, which says that if you have n vectors in Rn, right, so lists of n real numbers, and there are n of them, then we actually have a nice condition for establishing linear independence of those n vectors. So, drum roll, these n vectors are linearly independent if and only if what? The determinant of the matrix consisting of those n vectors is non-zero. Okay, that's the vector independence theorem. So now what do we have to say? What is a determinant, right? So this is the theorem, but now I have to tell you what is a determinant. How do you calculate a determinant? Once you do this, then you have a great way to tell if vectors are to show that linear vectors are linearly independent and also dependent, right? Because this theorem is if and only if. So if the determinant equals 0, then the vectors are linearly dependent. If the vectors are independent, the determinant is non-zero. It goes both ways, right? All right. So what then do we need to do? We need to look at what on earth is a determinant. So let's look in the dimension 2 case, right? So because it's a lot easier in the plane, right? In the plane, right? So in the plane, two vectors are linearly dependent. There we go. If and only if what? Well, if we want one vector to be able to be written as a scalar multiple of the other, there are only two of them, right? Well, the only way to do that is if the two vectors are on the same line, right? Because, here, say you have, say this is 3, 1. Well, you're only going to be able to write that as a scalar multiple of another vector if these two vectors are on the same line, right? Say if it were something like negative 1.5, negative 0.5, right? Then those two would be linearly dependent because they both lie on the line y equals 1/3 x, right? So that's how you get linear dependence in 2 dimensions. So they're linearly dependent if and only if they lie on the same line. Here's another way to say that. That is, if you have vectors AB and CD, right, those are linearly independent if and only if AB equals R times CD, right, for some R. Meaning one is a scalar multiple of the other. But look what we want here. I want linear independence to be equivalent to some quantity being non-zero. I want linear dependence to be equivalent to some quantity being 0, right? So how can I say that? What would have to be 0 if this were the case, right? Well, let's rearrange a little bit. What would I have if I rearranged here a little bit? I would have that um, A would have to equal RC, right? And B would have to equal RD. Those would have to be equal quantities, right? So if I then took these and I divided the equations, what would I get? I'd get AB equals RC over RD, right? Divide those equations. So now the R's cancel. AB equals CD, right? Then cross multiply. So you'd get AD equals BC, right? So these vectors are parallel. These vectors lie on the same line if and only if AD equals BC, which is to say, if and only if AD minus BC equals 0, right? This is, apparently I'm allergic to 2 by 2 determinants. Um, the, this is a quantity that is 0 if and only if these vectors are linearly dependent, right? Beautiful. So this gives us a formula, right? So you can say, okay, the determinant of a 2 by 2, A, B, C, D, then should equal A, D minus B, C, right? This is the quantity that is 0 if and only if those two vectors are, oh, and I wrote it transposed to A, B, C, D. It's it's the same, right? It's the same either way, because B times C and C times B are the same. But to be consistent with how I wrote these column vectors, right? There's V1, and then there is V2, right? But you can write it the other way too. You can transpose the matrix and it's the same. So there we go. There's our determinant. Okay, for 2 dimensions, right? All right. What about more dimensions, right? What if you have, say, 3, right? What if you have 3 dimensions? Then what would you do? Well, there is something called cofactor expansion, right? And cofactor expansion is, this is a recursive way to calculate determinants, where you can calculate um, a larger dimensional determinant in terms of a smaller. And in particular, you go down 1 dimension. So you can do an n by n determinant in terms of n minus 1 by n minus 1 dimension determinants. And here's how. Here's how you do that. So what you do, it's sort of a, looks like kind of a complicated process, but it ends up not being too bad. So um, what you do is you pick your favorite row or column in the matrix that you want to do cofactor expansion in. And it's kind of amazing, to be honest. It doesn't matter which row or which column you pick. Pick whatever one you like. So pick your favorite row or column, right? And what you do is you go through entries of that row or column one at a time. And here's what you do with those entries. What you do is you write down an alternating sum of those entries. And sometimes you start on a positive, sometimes you start on a negative. And you do that according to just a checkerboard. So the very top left entry in your matrix is always going to be positive, right? And then you just alternate from there, right? So that's the rule according to which you set the signs. And then what you do is you multiply each entry by the corresponding cofactor. And what the cofactor is it's the matrix with the row and column of that entry deleted. So this is why you get a recursion, because you delete a row, you delete a column. What's left has one less dimension. It's still square because you deleted a row and a column. So this is why you get an n by n determinant in terms of n minus 1 by n minus 1 determinant. So that's a mouthful, right? But I realize that's a lot to say. But in an example, I think you'll see it's not so bad. So for example, let's actually do this in an example. And let's use it the way we're not only going to do an example of calculating a determinant, but we're going to use it the way the vector independence theorem talks about it. So let's do 4 kind of ugly vectors. So let's say, are the vectors, I'm going to do big, ugly, messy vectors here. So I'm going to ask, are the vectors, how about 2, 0, 1, 0, right? So this vector, 1, 1, 1, 1, right? The all ones vector. Then minus 1, minus 1, 0, 1. Let's do all those. And let's do 0, minus 2, 1, minus 2. Right, let's take those 4 vectors. Right, so there, I want to know these 4 vectors. Are these vectors linearly dependent or independent? Which one? Right, that's what I want to know. And so I want, oh, and you know what? Pause. Yeah, there we go. So yes, so I have these 4 vectors, right? And I want to know, are they linearly independent or dependent? So what I'm going to do is I'm going to use this vector independence theorem. I'm going to calculate their determinant, the determinant of this 4 by 4 matrix, right? 2, 0, 1, 0, 1, 1, 1, 1, minus 1, minus 1, 0, 1, and then 0, minus 2, 1, 2. Right, this 4 by 4 matrix, I'm going to take its determinant. Okay, so let's see now here if we have a 0 determinant, in which case I'll conclude that they're dependent, or a non-zero determinant, in which case I'll conclude that they're independent. So, and this is a 4 by 4, right? So I'm going to calculate this by picking my favorite row or column, and then doing this alternating sum of cofactors, right? Multiplied by those entries. So what I'm going to do, I'm going to use right here, I'm going to use my favorite row or column is this. So I'm going to expand using the first column. And the reason I'm doing that, because it has 2 zeros, right? And when you're doing cofactor expansion, the more zeros, the better. because it will delete terms in your expansion. And now remember, we are going to use this sign chart, right? So this is the, for a 4x4, this is what it's going to look like, right? So when I do this, what am I going to have? I'm going to have the 2, I'm going to leave positive. So I'm going to do 2 times its cofactor. And then what's its cofactor? Well, you delete the row and column that the 2 lives in, right? So here I'm deleting the column and the row of 2, and then I'm putting the part that remains, that's the cofactor for that entry. Okay. Then what happens next? Now I'm going to use the next entry. I'm going to use this 0. And that one gets sign flipped. So I'm going to do -0 determinant of O. Well, I don't care. It's getting multiplied by 0, right? So technically that term is there. I put it there just for completeness sake, but don't even bother writing out the cofactor, right? It's 0. Okay. Then we'll do 1. So, and I do plus, right? So +1. Okay, this one I care about, right? And when you eliminate the row and column for 1, sorry, the row and column for 1, what's left? We write down the remaining entries. All right, there's the remaining 3x3. That corresponds to that entry 1. And then the last one, notice again, we have a 0. So it's 0, technically it's -0, times a determinant that I don't care about, right? Because it's a red shirt on this mission, right? So you don't bother remembering its name. So this is a cofactor expansion, right? It's a 4x4 determinant written now as a sum of 3x3 determinant. Okay. Then we do this again, right? We're going to do this exactly again. So now I have 2 times what? What's in here? Well, I'm going to expand along this middle row because, there's a 0 there, right? And remember the sign chart. So I'm doing -1 times the determinant of the remaining 2x2, right? Then we do +0 times I don't care. And then I'm going to do -1 times the determinant of the remaining 2x2. There we go. So there's that 3x3 unpacked, right? Then I'm going to do +1 times the determinant of this. And here I'm going to use the top row again because there's a 0. I want to pick something with a 0. So here I'm going to do 1, +1, times the determinant of the remaining 2x2, -1, -2, 1, 2. Then I'm going to do -1 times the determinant of its remaining 2x2, 1, 1, -2, 2. Then I'm going to do 0 times, I don't care. Okay. And now I'm down to the 2x2 case. Unfortunately, the 2x2 case we already figured out using geometry. That's just this AD minus BC formula. You do this diagonal minus that diagonal, right? 2x2s are nice and easy. So now I don't need to do cofactor expansion. Now I can just use the 2x2 formula. So I get 2 times negative, what is this? -2 plus 2, right? Then here I have minus, this determinant is going to be what? 1 plus 1, right? So that's our top one, right? Then what do I add to that? I add to that this next determinant is going to be what? 1 times -2 plus 2, right? And just to make it clear what I'm doing -2 plus 2, where you do AD minus BC, right? That's our what I'm calculating there. And then I have plus double negative, right? So it's plus 2 minus negative 2 is plus 2. Okay, so this is 2 times, I get 0 because those cancel, right? And then here I have negative 2. Now on this side I have what? I have 0 minus 2 plus 2, and then plus 4. So I get 2 times negative 2 plus 4. Ooh, that's negative 4 plus 4 is 0. So what did we just figure out? We just figured out that those 4 vectors, right, from the beginning of this problem, those vectors are in fact linearly dependent. Right? So this is perhaps, um, so this is a use of the vector independence theorem, perhaps a little surprising because it's not really easy at first glance to see what the dependence is. Um, so in fact, what is the dependence? Well, it turns out you can take one of these, right? None of these, um, two of these, and minus one of these. If you do all that, you get the zero vector. Right? That's why they're linearly independent. So there's the dependence, or odd dependence, right? You can also multiply both sides by anything. Let's see, did I do that correctly? I think so. In the first coordinate, you'd have 2 plus 0 minus 2. Yep, is 0. In the second coordinate, you'd have negative 2 plus 2 is 0. Yep. In the third coordinate, you'd have 1 plus 0 minus 1. And in the fourth, yes, this is correct. This is correct. Right, so there's our linear dependence. All right, so that's our, there's an example. Now, I have not proven this theorem, that this cofactor expansion always works for this idea of testing, any dimension of linear independence. Um, but it's true, right? It's a totally valid theorem, if and only if. And here's an example of it, right? So it's not a proof of the theorem at all, but a demonstration of applying the theorem to figure out what um, whether or not these vectors are dependent or independent. Okay, great. Thank you.